Hello, great friends. IBM is here with episode 7 of Superposition and Waves, or Waves and Superposition. And I think this is going to be the second last episode. I wanted them to be 8 because the questions are too many. So without wasting any time, I hope you are doing great. Let's move to episode 7. Let's go to our document. This is the document. I think we stopped in episode 6. We must have stopped on page 134. We stopped on this question, so I want us to start from 135. Noise reduction headphones actively produce their own sound waves in order to cancel out external sound waves. A microphone in the headphones receives waves of one frequency. A loudspeaker in the headphones then produces a wave of that frequency but of a different phase. What is the phase difference between the external sound wave and the wave produced by the loudspeaker in the headphones? That one is automatically 180 degrees. If the sound produced by the microphone or the sound produced by the headphones must cancel out external sound waves, then that should be destructive interference. Therefore, the two waves should have a phase difference of 180 degrees. In other words, we scientifically say they should be in what we call antiphase. Antiphase. So that is automatically 180 degrees. There is no need of calculating anything. Which statement about different types of electromagnetic wave is correct? The frequency of infrared waves is less than the frequency of blue light. I think that is true. From Rumenera's mother is visiting Uncle Xavier's garden. When you move from radio waves to gamma rays, here it is a frequency it is actual frequency which is increasing, which means here we have infrared. Infrared must be having a frequency less than visible light, and blue light is in under the visible light, the visible spectrum. This is where we have blue light. So it means the frequency of infrared is less than the frequency of blue light. Orange light has wavelength 600 nanometers. What is the frequency of this light? So if it is light, so we know the speed. So frequency is going to be the speed divided by lambda, which will be 3.0, which will be 3.0 times 10 power 8 divided by the wavelength, which is 600 nanometers, that is times 10 power negative 9. So we can check 3 exponent 8 divided by 600 exponent negative 9. So that is 5 times 10 power 14. 5 times 10 power 14. So it means B is wrong and A is also going to be wrong. So let's check C and D. We can change it to tera. Tera is 10 power 12. So I will divide by 1 exponent 12, which is 500. So our answer is going to be C. Electromagnetic waves of wavelength lambda and frequency f travel at speed c in a vacuum. What describes the wavelength and speed of electromagnetic waves of frequency f over 2? So we know that for waves c, which is the speed, is equal to lambda times f. What describes the wavelength and speed of electromagnetic waves of frequency f over 2? Remember, the speed does not change. So the speed remains c. That means we have eliminated the 2c and c over 2. The speed is constant for electromagnetic waves. But let's check the wavelength. So the wavelength is going to be c divided by where there is f. I'll put there f over 2. So this is f over 2, which means the 2 goes up. So it becomes twice c over f. Remember, c over f was just, this was lambda 2. Let this be the initial lambda. So this is twice the initial wavelength, because the initial wavelength here is lambda equals to c over f. So the new wavelength is twice c over f, which is twice lambda. So the wavelength is going to be twice lambda, so the answer is going to be C. When the liquid crystal display of a calculator is observed through a polarizing film, the display changes as the film is rotated. Which property describes the radiation from the calculator display? the display changes as the film is rotated. So which property describes the radiation from the calculator? Unpolarized, they are polarized. Longitudinal, they are not longitudinal. Transverse, it is a transverse wave. So the display, because the display changes as the film is rotated, it means the intensity which is passing through the polarizing filter is changing as the display is rotated. That is, as the axis of transmission is changed. So that is the property of transverse waves. A sound wave has a displacement y at distance x from its source at time t, which graph correctly shows the amplitude and wavelength. So amplitude and wavelength, so we shall ignore d because it is against time, and c because it is also against time. So we shall concentrate on A and B. Amplitude is distance in a specified maximum distance from equilibrium position in a specified direction. So this one is not the amplitude, but this is amplitude, and that is wavelength. So our answer is going to be B. A parallel beam of red light of wavelength 700 nanometers is incident normally on a diffraction grating that has 400 lines per millimeter. What is the total number of transmitted maxima? Total number of transmitted maxima. Remember, it is a diffraction grating. At this point, we now know that for a diffraction grating, n lambda is equal to d sine theta. I want you to draw a clear difference between a diffraction grating and a double slit. Every time I say diffraction grating, I'm using this formula, and every time I say double slit, I'm using lambda is equal to ax over d. So do not confuse these ones, and you use for the one for double slit in the place of diffraction grating. So when n is maximum, total number, when n has reached the maximum number, sine theta is equal to 1. So when sine theta is going to be 1, so n is going to be d divided by wavelength. But remember, d is equal to 1 over the number of lines per meter. This is number of lines per meter. Since they gave us number of lines per millimeter, we shall change it to per meter to be 400 times 1000, because 1 meter is 1000 millimeters. So it means we have 400,000 lines per meter. So now I'm substituting. N is going to be, where there is d, I put 1 over n, so that's 1 over 400,000, then times 1 over lambda, which is 700 times 10 power negative 9. So we now do the substitution, or we press our calculator. So I'll simply say 1 divided by, open brackets, 400,000 times 700 exponent negative 9. So that is giving us 3.57 recurring. So that is approximately 3.6. But remember, these are diffraction orders, so we round off the smallest whole number. So instead of writing 3.6, I'll round off to 3. So n maximum is 3. But remember, we want the total number of transmitted maxima. Total number of transmitted maxima. So to find the total number of transmitted maxima, I can demonstrate this as I did previously. Let's say this is the diffraction grating, this is the screen. There is a central, this is a grating, this is the grating, and this is the beam of light. There will be a central bright fringe, which we call the zero order, that is 1. Then we shall have n equals to 3 this side and n equals to 3 the other side. So we have 3 plus this 1 plus this 3. That gives us, of course, here there is 1, 2 up to 3, 1, 2 up to 3. So 3 up, 3 below, plus the central bright fringe, giving us a total of 7. So the answer is going to be 7. A signal that repeats periodically is displayed on the screen of a cathode ray oscilloscope. The screen has 1 centimeter squares, and the time-based setting is 2 milliseconds per centimeter. What is the frequency of this periodic signal? So let's just look for one complete cycle for this signal. Okay, so if I decide to start from this peak here, the next time I reach the same peak, it means that will be one cycle. So one cycle stops here. This will be the second cycle. So this is going to be 1, 2, 3, 4, 5 centimeters represent one cycle. So 5 centimeters are giving us one cycle or one period. So that means the period, remember, is the length of one cycle times the time-based setting. So the period is going to be 5 centimeters times 2 times 10 power negative 3. That is seconds per centimeter. So per centimeter cancels. So this is 10 times 10 power negative 3. Now I can find a frequency. The frequency is going to be 1 divided by the period, which is 1 divided by 10 times 10 power negative 3. So from my calculator, this is 1 divided by 10 exponent negative 3, which gives us 100. So our answer here is 100. Which statement about light wave and sound wave is correct? We know light waves are transverse and they are electromagnetic. Sound waves are longitudinal. Electromagnetic waves undergo polarization. So when we say both can be polarized, that is not true. Longitudinal waves cannot be polarized. Both can travel through free space. Sound does not travel through a vacuum, so that is also wrong. Both have frequency inversely proportional to wavelength. Of course, they both follow this equation, V is equal to lambda times F, which means F is inversely proportional to wavelength if V is constant. So the answer is going to be C. Both have an intensity proportional to the amplitude. That is not true. We know that intensity is directly proportional to amplitude squared. It should be amplitude squared. The sound from a loudspeaker placed above a tube causes a resonance of the air in the tube. A stationary wave is formed with two notes and two antinodes. Two notes, this is one, that is two. Two antinodes, there is an antinode here and an antinode there. The speed of sound is 330. What is the frequency of the sound? So we see that the length of the pipe is 60 centimeters, but this is a half a cycle plus a quarter. So it means the length of the pipe, which is 60, is equal to a half a cycle plus a quarter, that is 3 over 4 of wavelength. So it is 3/4 of a cycle. So that means the wavelength is going to be 4 times 60 divided by 3, which is 20 times 4, which is 80 centimeters. So from V equals to lambda times F, it means the frequency is going to be V, which is 330, divided by F, lambda, which is 80 times 10 power negative 2. So we can check 330 divided by 80 exponent negative 2. So that gives us 412.5, which is approximately 413. So our answer is A. Light of wavelength lambda passes through a diffraction grating with the slit spacing d. A series of lines is observed on a screen. So the diagram is here. Remember, for a diffraction grating, the angle we consider in the formula is always measured from the central bright fringe. So this is the angle theta. What is the angle alpha between the two first order lines? So let's first find theta. So we know that for a diffraction grating, n lambda is equal to d sine theta. N is 1, then times lambda equals to d sine of the angle theta. But remember, theta is alpha over 2. So it means lambda, of course, 1 has no significance, is equal to d sine alpha over 2. What is the angle alpha between the first order lines? So theta is alpha divided by 2. So sine inverse alpha divided by 2 is equal to the sine inverse of wavelength divided by d. So it means alpha is going to be twice sine inverse of alpha divided by d. So it means our answer in this case is going to be D. When plane polarized light of amplitude A is passed through a polarizing filter as shown, the amplitude of the light emerging is A cos theta. The amplitude of the light emerging is A cos theta. Okay. The intensity of the initial beam is I. What is the intensity of the emerging beam, emerging light when theta is 60 degrees? So initially, the amplitude, the intensity of the initial beam is I. So I will say intensity transmitted I1 is going to be I cos squared theta, where theta is the angle between the axis of transmission and the vertical in this case. So they have told us theta is 60 degrees. What is the intensity of the emerging light when theta is 60 degrees? So we shall just substitute. Here it is in terms of I, so I'll simply say I1 is going to be I cos squared, because they said when plane polarized light of amplitude A is passed through a polarizing filter as shown, the amplitude of the light emerging is A cos theta. So I'll just substitute here cos squared of 60, cos squared of 60 degrees. And this is going to give us so that is cos 60 and squared, that is 0.25 I. So here the answer is going to be 0.25 I. So the answer is going to be A. Electromagnetic waves from an unknown source in space were found to be significantly diffracted when passing through gaps of the order 10 power negative 5 meters. Without any hesitation, you notice that 10 power negative 5 is approximately infrared. Let's see the question. Which type of wave are they most likely to be? That is automatically going to be infrared waves. If you can't comprehend that, you go back to the electromagnetic spectrum. Menela's mother is visiting Uncle Xavier's garden. Here we have visible light, which ranges between 7 times 10 power negative 7 to 4 times 10 power negative 7. Remember, this is red, this is ultraviolet, then this is violet. So infrared, I can go on adding 2 to the power of 10. So here I have 10 power negative 7, I add a 2 there, it becomes 10 power negative 5, I get infrared. Then 10 power negative 5, I add a 2 on the power, it becomes 10 power negative 3, which is approximately micro. Then I can add plus 2 again, I get 10 power negative 1, which is automatically radio waves. On the right hand side of the visible spectrum, you can go on subtracting the powers. For example, to get ultraviolet, I can say 10 power negative 7 minus 2. That gives me 10 power negative 9. But even negative 8 is fine. Then for X-rays, I can again go say 10 power negative 9, again minus 2, it becomes negative 11. For gamma rays, I can say 10 power negative 11, again minus 2, it becomes negative 13, and so on and so forth. The graph shows how the height of a water surface at a point in a harbor varies with time as the wave passes the point. What are P and Q? So of course we know P is just displacement, it is not amplitude. Amplitude would be here, maximum displacement. So it is just displacement. So where we see P quoted as amplitude, that would be wrong. Then this point here is perfectly identical to this one. They are in a phase, so the distance Q must be wavelength. So our answer is going to be B. Displacement, no, because this is time. That will not be wavelength. So this is going to be A, because they gave us mean height against time. So that is going to be period. So displacement and period. The three waves shown in each diagram have the same amplitude and frequency but differ in phase. They are added together to give a resultant wave, in which case is the resultant wave 0. So, of course, by elimination, you notice that these waves, there is no way they will add up to give total displacement 0, because the displacements are almost on the same side or above the origin. So it means there is no way they will add up to give 0. So this is out. Similarly, this one here at the same in the same range, you see that the displacements are on the above the horizontal line. So this one will not give us 0. This one will be wrong because these two, when they add up here, they give a larger displacement. Yet at the bottom, we have a displacement which is a half of this one. So it means there will be no total cancellation. So this is also wrong. So the answer will be A. You notice that this is almost half of half of this. It is almost half. But remember, these two waves are meeting at this point. That means when they add up, they form a bigger displacement, which is almost the same as the other one. So it means when they form that bigger displacement or amplitude, it is going to cancel out the other one up, so that would give us 0. So our answer is going to be A. A stationary sound wave has a series of nodes. The distance between the first and the 60th node is 30 centimeters. What is the wavelength of the sound? So they gave us the distance between the first and the 60th node. If you are poor at dealing with this, then of course you can try to estimate. You can do this manually. So let's have 6 nodes here. 1, 2, 3, 4, 5, 6. So these are 6 nodes. 1, 2, 3, 4, 5, 6. So the distance between the first and the 60th node is 30 centimeters. So you want only to find the wavelength. So wavelength is going to be, so this is 1 wavelength, 2 wavelengths and a half. There are 2 wavelengths and a half in 30 centimeters. So we have 2 and a half, that is 5 over 2. So 5 over 2 wavelength is equal to 30 centimeters, which implies that wavelength is equal to 30 times 2 divided by 5. 30 times 2, that is 60, divided by 5, that is 12. So our answer is going to be 12 centimeters. What is meant by diffraction? Diffraction is spreading. Addition of two coherent waves to produce a stationary wave, that may not be diffraction. Bending of waves around an obstacle, that is automatically diffraction. Spreading around an obstacle or spreading through into regions of geometrical shadow as a wave passes through a narrow slit. Two waves E and G are shown. The waves never have the same speed. Which statement is correct? So it is displacement against time. Displacement against time. They have the same speed. So let's first check the wavelength or the frequency. So you notice that the frequency of this wave is greater than the frequency of this one, because we have more cycles in 3 milliseconds than this one here. So it means the frequency of wave G, if this is G, frequency of wave G is greater than frequency of wave E. That means the wavelength of G should be less than the wavelength of E. So wave E has a greater amplitude than wave G. Let's compare the amplitudes. So by sight, you notice that the amplitudes are almost the same. By sight, the amplitude is the same, so this is not going to be true. Wave E has a greater intensity than wave G. Intensity is directly proportional to amplitude squared, but they have the same amplitude, so this is not true. The intensities are equal. Wave E has a smaller frequency than wave G. That is automatically true. Wave G has a greater frequency than wave F. So wave E has a smaller frequency than wave G. The diagram shows a displacement time graph for a progressive wave. What are the amplitude and frequency of the wave? Amplitude, this is displacement against time, so amplitude is 5. So we ignore C and D. Then frequency, it is about amplitude against period. So frequency is going to be equal to 1 over period, which is 1 over. So we have from 5 to 25, that is 20. I hope it is not a stationary, it is a progressive wave. So this is going to be period 20 times 10 power negative 3. So 1 divided by 20 exponent negative 3. That is 50. So our answer is going to be B. Amplitude is 5, frequency is 50. Which observation indicates that sound waves are longitudinal? Sound can be reflected from a solid surface. Even light can. Sound cannot be polarized. Sound is diffracted around corners. Even light can, but that doesn't show that it is longitudinal. Sound is refracted as it passes from hot air to cold air. So the answer is going to be B. Sound cannot be polarized. This is what indicates that it is longitudinal. The vibrations cannot be confined in any other plane because the vibrations of the particles are parallel to the direction of propagation of energy. So there is no way you can confine them to another plane. They are already in one plane. To produce a stationary wave, two waves must travel in opposite directions through the same space. Which statement about the properties of the waves must also be true? The waves must have equal frequency but different speeds. The speeds must be the same. The waves must have equal speed but different wavelength. The wavelength must also be the same. The waves must have equal speed, frequency, and wavelength. So that is very true. The wavelengths, the speed must be the same, frequency must be the same, and the wavelength. Of course, if speed and frequency are the same, it implies the wavelength is the same. A surveyor device emits a laser pulse. What is the time taken for the pulse to travel from the device to a wall 150 meters away, where it is reflected and then returned to the device? It is reflected and then returned to the device. So time is going to be equal to distance over speed. It is light, I think. It's a laser produces light. So this is going to be distance over speed. Time will be distance over speed, that is over c. So the distance is going to be twice because they are saying where it is reflected and then returned. What is the time taken for the pulse to travel from the device to where it is reflected and then returned? So the distance is going to be 2 times 150 divided by the speed, which is 3 times 10 power 8, speed of light. So this is going to be 2 times 150 divided by 3 exponent 8. So that is 1.6 times 10 power negative 6, and that is 1 microsecond. So this is 1.6, 1.0 times 10 power negative 6 seconds, which is 1 microsecond. So the answer is going to be D. The period of an electromagnetic wave is 1 nanosecond. What are the frequency and wavelength of the wave? Since it is electromagnetic, the speed is the speed of light. So it means we know V is equal to lambda times F. V is therefore equal to lambda because F is 1 over T, so that is 1 times lambda over T. So it means the wavelength is going to be equal to the speed, which is 3 times 10 power 8, then times the period, which is 1 times 10 power negative 9 because it is nano. So 3 exponent 8 times 1 exponent 9, exponent negative 9. So that is 0.3. So the wavelength must be 0.3. So this is wrong, this is wrong, this is wrong. So our answer is automatically C because the wavelength is 0.3. X and Y are 2 points on the surface of water in a ripple tank. A source of waves of constant frequency begins to generate waves, which then travel past X and Y, causing them to oscillate. What is the phase difference between X and Y? What is the phase difference between X and Y? Let me try to draw a horizontal line here. Okay, so X is vibrating vertically upwards. Y could be vibrating downwards or at rest because it is at maximum displacement. So, but X is at equilibrium position and Y is at maximum displacement. We can calculate this to be very accurate. Phase difference is going to be 360 divided by the distance between the two particles compared to the wavelength. So in terms of wavelength, let's see. One wavelength stops here, so this is a half plus a quarter. So X is a half plus a quarter of a wavelength, which is going to be 3/4 of a wavelength. So it means the phase difference is going to be 360 into 3/4 of a wavelength divided by wavelength. So wavelength has cancelled out. So I have just 360 times 3 divided by 4, which is 270. So my answer is going to be D, 270. Or I could also add one cycle on 270. So in sometimes it might be, you might find that you get 270 plus 360. It could also be the same. So 360 plus 270. The phase can also be 630 and so on and so forth. Just go on adding one complete cycle. A monochromatic plane wave of speed c and wavelength lambda is diffracted at a small aperture. The diagram illustrates successive wavefronts. So this distance is going to be wavelength. Of course, this one is also still wavelength. This is also still wavelength. So after what time will some portion of the wavefront xy reach point P? So xy will reach point P after covering a distance which is 3 times wavelength. So distance is 3 lambda. And it is a wave which is a monochromatic. Of course, the word monochromatic refers to light. So the speed is c. So the time is going to be distance divided by speed c, which makes the answer to be C. A standing sound wave is set up between a loudspeaker and a wall. A microphone is connected to a cathode ray oscilloscope and is moved along a line directly between the loudspeaker and the wall. The amplitude of the trace on the CRO rises to a maximum at a point X, falls to a minimum, and then rises once again to a maximum at point Y. The distance between X and Y is 30 centimeters. Of course, if it raises to a maximum, there's a maximum at point X, and the next maximum is at point Y. So this one is going to be wavelength. The distance between two successive maximum points is most likely going to be a wavelength. The speed of sound is 330, which diagram represents the CRO trace of the sound received at X. The time base is 0.5 milliseconds per centimeter. Okay, let's check. So we have the wavelength as that. Let's first just find the period. So period is going to be equal to because V is equal to lambda F, which is equal to lambda over T. It means T is lambda divided by V. So this is going to be lambda, which is 33 times 10 power negative 2 divided by V, which is 330. So the period is going to be 33 exponent negative 2 divided by 330, which is 1 times 10 power negative 3, which is 1 millisecond. That is 1 millisecond. So that is the period. Let's find the length of the cycle representing length of the wave representing one cycle. So period is going to be equal to the length of the wave representing one cycle times the time base setting X. So let's check. We are just looking for L. The period is 1 millisecond. L is not known, but the time-based setting is 0.5 milliseconds per centimeter. So this is milliseconds, so seconds and m cancels out. So you notice that L is going to be equal to 1 divided by 0.5, and this will be in centimeters. So 1 divided by 0.5, I think that is 2. So L is 2 centimeters. So the length representing one cycle should be 2 centimeters. So let's check. This is, of course, one cycle is taking more than 2 centimeters. This is one cycle is taking 1, 2, 3, 4 centimeters. So these two are already wrong because one cycle is taking more than 2 centimeters. Here, one cycle is taking more than 2 centimeters. And here we see one cycle is taking 1, 2 centimeters. So the answer is going to be D. The diagram shows an air-filled pipe open at both ends. The length of the pipe is 1 meter and the lower surface of the inside of the pipe is covered with a layer of fine sand. When a source of sound is of a single frequency is put near one end of the pipe, the air in the pipe is found to resonate, and a pattern in the sand shows that a standing wave containing 3 nodes is formed within the pipe. So let's have 3 nodes in the pipe. Of course, we can't have a node at the open end. So I'll have here 1, let's have here 2, 3. So that means if I was to trace in a wave, I would do something like this. Okay. The speed of sound in air is 330 meters per second. What is the frequency? So the length of 1 meter is going to represent this part here is that is 1 cycle, a quarter plus a quarter, that is half a cycle. So 1 plus half a cycle is going to be that is 3/2 of wavelength. So this is a half plus a half plus a quarter plus a quarter, that is 1 cycle plus a half a cycle, which is 3/2 wavelength. So 3/2 of wavelength is going to be 1 meter, which means the wavelength is going to be 2 divided by 3 in meters. We just cross multiply. So frequency is going to be equal to V over wavelength, which is going to be 330 divided by wavelength, which is 2/3. That gives us 330 times, we get the reciprocal, 3 divided by 2. So 330 times 3 divided by 2. That is 495. So our answer will automatically be B, 495. A stationary sound wave is formed in a measuring cylinder by blowing across the top as shown in the figure. What statement is correct? The fundamental frequency of the stationary wave decreases when some water is added to the cylinder. Which statement is correct? A stationary sound wave is formed in a measuring cylinder by blowing across the top as shown. Which statement is correct? Of course, if the other end is closed, it means the length of the pipe here would be equal to a quarter of a wavelength, which means that the wavelength would be equal to 4 times L. Now, if we put in some water, they said a stationary sound wave is formed in a measuring cylinder by blowing across the top. Which statement is correct? The fundamental frequency of the stationary wave decreases when some water is added to the cylinder. Of course, if we add some water here, we reduce L. When L decreases, it means our wavelength has decreased. And we know that wavelength is inversely proportional to frequency. That means the frequency has increased. So this one, the fundamental frequency decreases, that one will be wrong. The stationary wave in the cylinder is caused by superposition of two waves moving in opposite directions. That is correct. A stationary wave travels from the open end to the closed end and it undergoes reflection. When the incident and reflected waves meet, a stationary wave is formed. So that is going to be B. Diffraction can be observed when a wave passes an obstruction. The diffraction effect is greatest when the wavelength and the obstruction are similar in size. For waves traveling through air, what is the combination of wave and obstruction that could best demonstrate diffraction? For waves traveling through air, what is the combination of wave and obstruction that could best demonstrate diffraction? Microwaves passing a steel post, radio waves passing a copper wire, sound waves passing a human ear, visible light waves passing a gate post. So here this will not show good diffraction because visible light have a very small wavelength. Sound waves passing a human ear. This may not necessarily demonstrate diffraction because the sound waves, if you try to find the wavelength of sound, is relatively longer than the size of the of what of that part where the sound waves passing a human ear. The wavelength of sound is is much bigger than the human ear, so this will be out. Radio waves passing a copper wire. Wavelength of radio waves is much larger than the copper wire, about 10 power 2. So microwaves passing a steel post. Remember, microwaves is around 10 power negative 2 meters, and the diameter of a steel post can also be very close, 10 power negative 2. So this is going to be A. A healthy inspector is measuring the intensity of a sound near a loudspeaker. His meter records an intensity I, that is near. This corresponds to an amplitude A. So when intensity is I, the amplitude is A. So we know that intensity is directly proportional to amplitude squared. This means intensity I is equal to K times A squared. At another position, the meter gives an intensity reading of twice I. Now when the intensity is twice I, this is equal to a constant times the new amplitude, which I will call A2 squared. Now we combine these two equations. So I can just substitute for I in the second equation here, which means 2 into where there is I have K A squared is going to be K A2 squared. So K cancels. I want to make A2 the subject, so I find the square root. So A2 is going to be A times the root of 2, or root of 2 times A. So our answer here is precisely going to be B, root of 2 times A. That is the new amplitude. The diagram shows a graph of displacement against time for a sound wave. The intensity of the sound is halved. If the intensity is halved, which graph shows the displacement of this sound wave? The intensity is halved, the period is not affected. The intensity is halved, the period is not affected, so the period should remain the same. This one is showing a change in period. This one is also showing a change in period. This one is showing the same period. Yes, this is the same period. This is the same period. Let's now check the period. Intensity is equal to a constant times amplitude squared. In other words, intensity is directly proportional to the amplitude squared. So if for the first one it is A, which is represented by 1, 2, 3, 4, let's say A is 4. So first intensity I is equal to K times 4 squared. Let me just call the number of boxes just 4 squared. Then for the second one, the intensity is halved. So where there is I will put a half I is equal to K. The new amplitude I will just call it A2 squared. So we combine these two equations. So I will say a half, where there is I will put the value of I, which is K times 4 squared, should be equal to K times A2 squared. So K cancels. 4 squared is 16 over 2, that is 8. So 8 is going to be equal to A2 squared. That means A2 is going to be the square root of 8. And the square root of 8 is 2.8, approximately 3. So this is going to be very close to 3, very close to 3 boxes. So this one is showing 2 boxes, so this is wrong. This one is close to 3 boxes, so the answer is going to be D. What do not travel at the speed of light in a vacuum? Electrons, microwaves, radio waves, X-rays. So that is electrons. The rest are electromagnetic waves, so they travel at the speed of light in a vacuum. A musical organ produces notes by blowing air into a set of pipes that are open at one end and closed at the other end. What is the lowest frequency of sound produced by a pipe of length 10 meters? The pipe blowing air into a set of pipes that are open at one end and closed at the other end. So the fundamental mode will give us such an illustration. That means the length of the pipe L represents a quarter of wavelength. That is in the fundamental mode. The length has been given as 10, so it means 10 meters is equal to a quarter of wavelength. So wavelength is going to be 40 in meters. So we can find the frequency. Frequency is equal to V over lambda, which will be 320 divided by lambda, which is 40. So 320 divided by 40, that gives us 8. So the frequency is going to be 8 hertz. So the answer is going to be B. A cylindrical wire of length 10 meters and diameter 2.0 millimeters has a resistance of 0.05 ohms. For which material is the wire made? Of course, this is not waves, but I will still answer it. The length is this, so diameter is that, resistance is that. So for which material is the wire made from? So we know the resistance is equal to rho L over cross-sectional area, and we know area is pi d squared divided by 4. So this becomes 4 times rho L over pi d squared. That is if I remove A. So we can try to check the resistivity. Resistivity will be equal to R times pi d squared divided by 4 times L. We substitute 0.05 times pi times d, which is 2 times 10 power negative 3, and this is going to be squared, divided by 4 times 10. So we have this as 0.05 times pi, then times, open another bracket, 2 exponent, negative 3 squared, then divide by 40. That's 1.6 times 10 power negative 8, which is a silver. So this is 1.6 times 10 power negative 8 meters, and that is silver. Diagram shows two identical loudspeakers driven in phase by a common audio frequency. When a student moves along line X, Y, she notices that there are variations in the loudness of the sound. The regions in which the sound is heard are alternately loud and quiet as indicated on the diagram. How may the distance between loud regions be reduced? That is automatically X. So this is acting as like a double slit. So lambda is equal to AX divided by D. How may the distance between loud regions be reduced? So we want to reduce X. We have two options. We either reduce lambda, because lambda times D is equal to AX. We reduce lambda, we reduce D, and we increase A, because we notice that A is inversely proportional to X. Therefore, decrease the distance A. Decreasing A increases X, yet we want to reduce it. That is wrong. Increase distance D. D is the distance between the speakers and the screen. If we increase D, it increases X. So this will also be wrong. Increase the frequency of the audio frequency source. If F increases, it means lambda decreases. And when lambda decreases, X also decreases. So it means the answer is going to be C. A horizontal glass tube closed at one end has a layer of dust inside it on its lower side. Sound is emitted from a loudspeaker that is placed near the open end of the tube. The frequency of sound is varied, and at one frequency, a stationary wave is formed inside the tube so that the dust forms small heaps. The distance between 4 heaps of dust is 30 centimeters. 4 heaps of dust is 30 centimeters. Remember, wherever we have a dust, we have a node, because that is the point where particles are under minimum, they're actually under maximum pressure. So this is a node, that is another node, there is a node here, there is a node there. So this is the distance between 4 nodes. Okay, so the speed of sound in the tube is 30. You notice that this wavelength is 1.5. So 30 centimeters is equal to 1.5, that is 3/2 wavelength. This is a half plus a half plus a half, that is 3 halves wavelength, which means the wavelength is going to be 2 times 30 divided by 3, which is 10 centimeters, or that is 60 divided by 3. No, not 10, that is 20 centimeters. So what is the frequency of the sound emitted by the loudspeaker? So frequency is going to be V over lambda, where V is 330 divided by lambda, which is 20 times 10 power negative 2. So that is 330 divided by 20 exponent negative 2. That is 1650, which gives us the answer as A. The diagram shows a cathode ray oscilloscope display of an electromagnetic wave. The time-based setting is 0.2 microseconds per centimeter. So they have showed us that this distance is 1 centimeter. That means this is also 1 centimeter. This is also 1 centimeter. So our wavelength is going to be equal to, the wavelength here is going to be equal to 2 centimeters. Which statement is correct? The frequency of the wave is 2.5 megahertz. Let's check. Frequency is going to be 1 over period, which is 1 over. Period is going to be length of one cycle, which is 2 centimeters times 0.2 times 10 power negative 6. So we have 1 divided by 2 times 0.2 exponent negative 6, which gives us 2.5. We have, this is 1, 2, 3, 4, 5, 6, 2.5 megahertz. So the frequency is 2.5 megahertz. This is showing the frequency is 5, so ignore C and D. The frequency is 2.5 megahertz and it lies in the radio wave region. Because the wavelength is 2 centimeters, 2 centimeters is 0.02 meters, and 0.02 is automatically radio waves. That is 2 times 10 power negative 2. It is either radio waves or two divided by 100, that is 0.02 in meters. That is either, it is going to be either radio waves or microwaves, but most likely it is going to be radio waves, because I said if for visible it is 10 power negative 7, for red we add a 2, it becomes 10 power negative 5, that is infrared. We add a 2, it becomes 10 power negative 3, that is microwaves. So 0.02 meters is more of radio waves than microwaves. So the answer is going to be A. The diagram shows a trace of a wave of a cathode ray oscilloscope. The vertical grid line have a spacing of 1 centimeter. The voltage scaling is 4 volts. The time scaling is 5 milliseconds per centimeter. What are the amplitude and period of the wave? So for amplitude, I will just count peak to peak. 1, 2, 3. 3 divided by 2, that is 1.5 centimeters. So the amplitude should be 1.5 times the setting, which is 4. That gives us, I think, 6.0. Let's check. 1.5 times 4, that is 6. So the amplitude should be 6. So without even further calculation, there's only one amplitude of 6. So the answer is C. Which statement about sound waves in air at constant temperature is correct? Sound waves. Amplitude is inversely proportional to velocity. That is not true. Frequency is inversely proportional to wavelength. That is very true. From V is equal to lambda F. Lambda is inversely proportional to F. So the answer is B. Frequency is inversely proportional to wavelength. The source of sound of constant power P is situated in an open space. The intensity I of sound at distance R from this source is given by that equation. How does the amplitude A of the vibrating air molecules vary with the distance R from the source? Okay, this is a simple equation. We know that power is constant, 4 pi is constant, so I is inversely proportional to R squared. But we also know that I is directly proportional to amplitude squared. So when we combine these two equations, it means amplitude squared is directly proportional to 1 over R squared. And when we remove the square root both sides, it means A is directly proportional to 1 over R. So that means our answer is going to be A. Which electromagnetic wave phenomenon is needed to explain the spectrum produced when white light falls on a diffraction grating? Of course, when white light falls on a diffraction grating, the light splits through, forming a bright spot which is white at the center, and interference patterns above and below. So coherence, not at all. The answer is going to be interference. This can't be polarization, it can't be refraction. So it is interference which is forming those interference patterns. A diffraction grating with 500 lines per millimeter is used to observe diffraction of monochromatic light of 600 nanometers. The light is passed through a narrow slit, and the grating is placed so that its lines are parallel to the slit. Light passes through the slit and then the grating. An observer views the slit through the grating at different angles, moving his head uh, from X parallel to the grating through Y, opposite the slit to Z, parallel to the grating on the opposite side. How many lines of the slit does he see? Already this is 1. At the position Y, there is a pattern there. So let's check the remaining ones. Using n, lambda is equal to d sine theta. Remember, when n is maximum, sine theta is equal to 1. So we want n is going to be d divided by lambda, because sine theta is equal to 1. We know that sine theta is equal to 1 because n is maximum. And we also know that d is 1 over the number of lines, but n must be number of lines per meter. So we just substitute n is going to be d. Where there is d, I will put 1 over. Number of lines is 500. We change it to lines per meter, that is times 1000. Then divide by wavelength, which is 600 times 10 power negative 9. So this is going to be 1 divided by 500,000 times 600 exponent negative 9. So that gives us n as 3.33 recurring. So we just round off to 3. So it will have x3 up and 3 below. giving us a total of 3 plus this 1 plus 3, that gives us 7. The time base on a CRO is set to 6 milliseconds per centimeter. A trace consisting 2 pulses is recorded as shown in the diagram. What is the time interval between the 2 pulses? So the length representing the time interval is 4.5 seconds. So the time base setting is that one. So the time interval is going to be 4.5 centimeters times the time base setting, which is 6 milliseconds per centimeter. So per centimeter cancels. So 4.5 times 6, which gives us 27 milliseconds. So the time interval between the 2 pulses is 27 milliseconds. A particle moves in the manner shown by the velocity time graph. The displacement of the particle has been measured so that it is 0 at t equals to 0. So displacement is 0 at t equals to 0. Point Q refers to a point in its motion. So Q is a point in its motion where the velocity is maximum. So here the velocity is maximum. This particle Q must be passing equilibrium. Which row of the table is correct? When the velocity is maximum, remember, the displacement must be 0. Times for maximum displacement. Yes. So times for maximum displacement in seconds. Okay, we have A 2.5. 2.5 is here. That is true because at maximum displacement, at maximum displacement, the velocity is 0. When the velocity is maximum, displacement is 0. So that means time for maximum displacement, we have 0, 5, 10, 15, and 20. That is maximum displacement. So 2.5, 12.5 here. 2.5, 12.5, that is not true. 5 is correct. 15 is correct. 2.5, 12.5, that is wrong. So remain with the B and D. So 5 and 15, 5 and 15. Then let's check the acceleration. At Q, velocity is maximum. When velocity is maximum, the acceleration is 0. So I'm saying at Q, V is maximum. And when V is maximum, then A is 0. Acceleration is 0. So the answer is going to be D. In which order of magnitude are the frequencies of electromagnetic waves in the visible spectrum? So in the visible spectrum, we just try to find the wavelength. And we know that for the visible spectrum, the wavelength is approximately 10 power negative 7 in meters. So let's check which of these frequencies give us, or which one, if we use this wavelength, which frequency shall we get? So V is equal to lambda times F. F is going to be V because it's electromagnetic, that is 3 times 10 power 8, divided by wavelength, which is 10 power negative, it will be 10 power negative, negative 7. So if I choose a wavelength such as 4 times 10 power negative 7, that is maybe violet. So I'll have 3 divided by 4. That is 0.75 times 10 power 15, which gives us 7.5 times 10 power 14. So our answer is going to be C. So you can choose any value of wavelength in the visible range, but the power of 10 is negative 7. A transverse progressive wave, the wave is progressive, is set up on a string. The graph shows the variation with the time of the displacement for a point on this string. So it is displacement against time. The separation xy on the graph represents the dash and the dash of the wave. X and y equal and y have equal dash. The separation xy on the graph represents the dash of the wave. X and y have equal dash. So first of all, you see that they are at the same distance, the same displacement from the equilibrium. So they have the same displacement from the equilibrium, and this is time. So these are particles which have reached the same point in their cycle, and they are both vibrating vertically upwards. So they're in phase. So the distance between x and y must be representing period, because this is displacement against time. So that is period. So 1 is going to be period, and 2 is going to be displacement, not amplitude. Because it's a progressive wave, it is not amplitude, it is displacement. But if it was a stationary wave, it could be amplitude. So our answer here is going to be B. If a wave can be polarized, it must be longitudinal, no; sound, no; electromagnetic. Of course, electromagnetic can be polarized, but not only them. All transverse waves can be polarized, so the answer is going to be D. Electromagnetic is just a subset of transverse. In which situation does diffraction occur? A wave bounces back from the surface, that is reflection. A wave passes from one medium to another, it could be refraction. A wave passes through an aperture, so that is diffraction. The wave spreads into regions of geometrical shadow when it passes through an aperture. The diagrams show the arrangement of apparatus for a Young's slit experiment, and also part of the pattern formed on the screen with a ruler placed next to it. So you can see that diagram. So what is the wavelength of the light? What is the wavelength of the light? So they have given us the distance between one darker fringe and a bright fringe. So we may find the distance between two successive dark fringes, and that distance is going to be half wavelength. Distance between two bright fringes should be equal to half wavelength. Or distance between a darker fringe and the next dark fringe should also be half wavelength. Is that true? No. That one does will work for a stationary wave. Since it is a double slit, I will simply use lambda is equal to ax divided by d. Okay. So we are going to find x. So this distance is x, this is x, this is also x, and this is a half x. So you have x plus x plus x plus a half x. So you have 3x plus a half x equals to 30 minus 20, which is 10 millimeters. So what is x? So 3x LCM is 2. That is 6x plus 1, that is 7x, is equal to 10 millimeters. So that means x is going to be 20 divided by 7 millimeters. Okay, so the wavelength is going to be A, which is the slit separation, that is 0.9 times 10 power negative 3 times x, which is going to be 20 over 7 times 10 power negative 3 divided by d, which is 5. So 0.9 exponent negative 3 times 20 exponent negative 3 divided by 7 times 5. So that is 5.1 times 10 power 1, 2, 3, 4, 5, 6, 7. The power of course, the most correct answer here is going to be 5.4. So this is 5.4 times 10 power negative 7, because all these ones are far off from that. So this is because we have made an estimate here. It may not be exactly 5.1, but this is the most correct answer there. P is a source emitting infrared radiation, and Q is a source emitting ultraviolet radiation. The figures in the table are suggested values for the wavelengths emitted by P and Q. So P is ultraviolet, and ultraviolet after violet is going to be 10 power negative 8. So P is ultraviolet. P is a source emitting infrared. So this is Q. Q should be 10 power negative 8. So we eliminate D and B. Then the figures, P is infrared. Infrared is after red, it must be less than 10 power negative 7. So it could be 10 power negative 6, negative 5. So it means we shall eliminate this one because this one is in the visible spectrum. So our answer is going to be automatically A. The diagram shows a view from above of a double slit interference demonstration. L is a monochromatic light source with a vertical filament. B is a barrier with two narrow vertical slits, and S is a screen upon which interference fringes form. The intensity is I at a point on the screen where the center of the fringe pattern forms. What is the intensity at the same point when one of the slits is covered up? So they told us B is a barrier with two narrow vertical slits, and S is a screen upon which interference fringes form. The intensity is I at a point on the screen where the center of the fringe pattern forms. What is the intensity at the same point when one of the slits is covered up? Intensity at the same point when one of the slits is covered up. So when one of the slits is covered up, what is going to be the intensity? Remember, at point where the center of the fringe patterns forms, here the amplitudes are going to be added up. So the amplitudes here add up, and remember intensity is directly proportional to amplitude squared. So if the intensity here is I, if the intensity there is I, and yet the amplitudes added up, so the intensity there was intensity I was equal to a constant and the amplitudes added up, which is A plus A, and that is going to be squared. So I is going to be equal to K into twice A, and that was squared. So the intensity there was I, and the amplitudes added up. What is the intensity at the same point when one of the slits is covered up? If one of the slits is covered up, then the intensity arriving there, we call it I2, is going to be K into A squared, because only one slit will be providing the light there. So the intensity there, I2, is going to be K times A squared. Now we are going to combine these two equations. So I would say I2 divided by I is equal to K into A squared divided by K into twice A, and that is squared. Here at this point, waves travel the same distance, the amplitudes add up. So the K cancels, so we remain with the I2 being equal to the I goes up. In the denominator we have, of course, we have A squared there, divided by 4A squared, and A squared cancels. So our answer remains I over 4, meaning the answer here is going to be D. Traveling waves of wavelength 20 centimeters are created in the air column in a closed pipe P and an open pipe Q. The lengths of the pipes are shown. In which pipe or pipes are stationary waves formed? Of course, whether the pipe is closed or open, there is always a stationary wave. So we can say P and Q. A wave that can be polarized must be transverse. Of course, longitudinal cannot. Progressive, whether it is progressive and longitudinal, it will not. Stationary wave, as long as it's longitudinal, it is not. So it must be transverse. Lastly, for part 7, which statement about electromagnetic radiation is correct? Electromagnetic radiation. Waves of wavelength 5 times 10 power negative 9 meters are high energy gamma rays. Well, gamma rays have wavelength of about 10 power negative 13, 10 power negative 14, around there. So this is not true. Waves of wavelength 3 times 10 power negative 8 meters are ultraviolet. That is most likely going to be true because Rumenera's mother is visiting Uncle Xavier's garden. When we look at the visible light, the visible spectrum, here we have red, there we have violet, and violet is 4 times 10 power negative 7 meters, yet wavelength decreases in that direction. That is a decrease in wavelength. So it means ultraviolet should have a wavelength slightly below negative 10 power negative 7, which is 10 power negative 8. So the answer is going to be B. Okay, so that is the end of part 7. I'll see you in the last part, which will be part 8. I hope you learned something from this, and I wish you a good day. Bye bye.